Today we are talking about how to fake your way through most of the rest of your science coursework. Being able to think about problems, and particularly units, systematically allows you to fake your way through a lot of science courses. This doesn't work at all in Chem, which is a lot less math and a lot more potions, but I digress. Most of the math in this course is essentially high school algebra. Even those of you who may have struggled at the time probably know it better than you think you know it. I hope in this lesson to give you some tools to generalize the application of algebra-based problem solving in hopes that a little extra effort now will make the rest of your science career easier. I'm going to start out by reminding you of how much you know with a quick quiz. First question, what is 1 divided by 1? If you answered 1, great work. You're off to a great start. If you answered anything else, we should probably talk. Okay, next question is 2 over 2. And next, 3 over 3. And now, 4 over 4. See, more likely than not, you already know that anything divided by itself is 1. And it doesn't matter what it is. So, x over x also equals 1, no matter what x is. X doesn't even need to be a number. You can divide anything by itself, and it is still going to be 1. This is central to the problem solving in all sorts of basic science. If you start with a value, here we'll take 1.1 miles, the distance of our family's daily quarantine walks to feed the chickens dandelions at a nearby house. That value can be easily converted to an equivalent form. If we want to convert that number into feet, perhaps because a 4-year-old thinks that a larger number is a larger distance, we just need to make sure we get rid of the units and replace them with a new unit. If you want to get rid of anything in a multiplication problem, we just make it 1. So we know that if we multiply miles by something in the form feet over miles, the product will be feet times miles over miles, which you've already shown me and yourself that you know is just feet. We can't just multiply by random values. This conversion factor needs to have a value of 1. This way of thinking is really important because it makes up most of this class, most of the non-calculus based physics, and frankly allows you to problem solve problems that you've never seen before and don't have formulas that you can memorize. But that's great news because you already know the math behind this. Anything divided by itself is 1. It's really important to write down units at every step because when you do, you're able to follow a very simple set of rules for setting up conversion factors. First, just like we saw, if we know that we can convert miles to feet if we put miles on the bottom of a conversion factor and feet on the top. Since miles start out on the top, a mile on the bottom gives a unit value of 1. When we actually put in the value for the conversion factor, we need to make sure that the top and bottom are equal to each other so that the conversion factor has a value of 1. But this is fairly straightforward. If we know that 5,280 feet equals 1 mile, we can easily use that to make our conversion factor. If we divide both sides by 5,280 feet, we get 1 on the left side, 5,280 feet divided by 5,280 feet, and the right side becomes a conversion factor that we can easily use. Similarly, we could divide both sides by 1 mile, and we'd also have a conversion factor on the left and value of 1 on the right. Notice that we get 2 different but equivalent conversion factors. We can always flip a conversion factor over and it will still equal 1 as long as we flip both the number and the unit together. We can plug this into our equation and find out that 1.1 mile is 5,800 feet. You want to go on a really long walk? How about a 5,800 foot walk? That's really long. Notice that since the directions from Google I looked only told me 1.1 miles to 2 significant figures, I only know the number of feet to 2 significant figures as well. Of course, my kids wise up to me pretty fast, so we might need to convert inches from feet sometime soon. That's fine. We can string as many conversion factors together as we need. A 70,000 inch walk? How will we ever make it back for dinner? A 1.8 trillion nanometer walk? I think I might need you to carry me. You get the picture. If you can set up a problem as one unit being converted to another and set up the conversion factors correctly, this gets you through most of the general chemistry and makes it at least the first couple of years into parenting a lot easier. Until your kids learn dimensional analysis anyway. We're going to work through a few problems systematically so you can see how dimensional analysis works to solve whole problems in both common and unusual forms. I've listed 5 steps to problem solving, not because I expect you to distinctly write down every step every time you solve a problem, even though we will here. Delineating these steps gives you something to fall back on when you encounter a more challenging problem that you don't immediately know how to solve. Since we here at Trinity Christian College are trolls, the subject of our inquiries will be the Trinity troll. I imagine that the drink of choice for a real troll might be mead, and that they absolutely drink it at least a liter at a time in quantity. I only have micropipetters that measure in microliters in the lab, so how many microliters of mead corresponds to 17.6 liters, which, because troll still uses the customary system, is about 1 kenning. The problem here is hopefully clear. We need to do a metric conversion from liters to microliters. We only have 1 unit to work with to start, and so we need a conversion factor between the liters and microliters. We'll put liters on the bottom to cancel out the starting units of liters, and we'll put microliters on top. Of course, we'll also need to make sure that the top and bottom equal each other. Like we talked about before, there are lots of ways to make metric conversions work. I personally like the version where you make everything equivalent to the base unit, in this case 1 liter. So I'll put 10 to the 6 to go with a micro prefix worth 10 to the negative 6, and then set up the conversion factor like that. We want to write out our conversion factor in the units that we are converting so that we can make sure the math works out the way that it did in our head. We can see that the liters divide by liters to equal 1 as written, so good work us. When we do the math, we end up with 17.6 times 10 to the 6, which is a kind of awkward mismatch of almost scientific notation. It makes more sense to express fully in scientific notation by moving the decimal place once to the left and adding a power to make 1.76 times 10 to the 7th as shown. The way that I always check my work is by comparing the size of units. I know that there are many microliters in a liter, so my number should be going up. And it did, so we probably went the right direction with our conversion factor. Clearly, we are going to be pipetting for a while, but deep down, you always knew that a micropipetter was probably not the right tool to quench a troll's thirst, if not from a practical standpoint, at least from a metric of lab safety. Little known fact, trolls love to walk the Trin Trail through the forest. Less light, less people, and of course, every troll's favorite, bridges. From the entrance near 123rd to the other end near the back of the arc is about 0.25 miles, about a quarter mile, with the 5-digit very much estimated. Troll wants to know if Troll can use it for 100-meter sprint training, because Troll wants to join the track team in the spring. So again, we have a conversion, this time miles to meters. Our given is 0.25 miles. The conversion factor between miles and meters is not one that I would expect most people to know, so there are a lot of potential strategies. I might choose to string 2 conversions together by converting miles to feet and then feet to meters if I know both of those conversions. I could also start by converting miles to kilometers and then kilometers to meters. That's actually the conversion I know, so that's what I'm going to do. See if you can identify what goes on top and what goes on bottom in each of the 2 conversion factors, miles to kilometers and kilometers to meter. The first conversion we have is kilometers over miles. By putting miles on the opposite side, we end up with miles dividing out to 1. I happen to remember from Miss Stamis' 6th grade math class that 0.62 miles equals 1 kilometer. So I'll make sure that the 0.62 goes with miles and 1 with kilometers. The kilometer to meter conversion is a straight metric conversion. I put kilometers on bottom now to cancel out the kilometers that we made with the last conversion. And I make sure to multiply by 10 to the 3rd by the meters to balance the kilo that is also worth 10 to the 3rd. When I multiply it all out, I get 400 meters. Technically 402.366, but I can only keep 2 significant figures. If I don't want to put it in scientific notation, I can just draw a line over the last significant figure, like so. I know that the mile is bigger than a kilometer, so the kilometer number which would have been about 0.40, should be bigger than 0.25. So check there. We go to a much smaller number when we go to meters, or a much smaller unit anyway, that when we go to meters. So again, this number should be going up. 400 is definitely going up. So our solution seems reasonable. This, of course, is not the only way to solve this problem. We could also just look up a conversion from miles to meters, and that's a perfectly reasonable thing to do in a homework problem. We shouldn't just use Google Converter for this class because it sidesteps developing the problem-solving skills that we want, even though that is absolutely reasonable in some contexts. Unfortunately, not all of life's problems, or even Troll's problems, are quite so simply set up. Troll has a notorious love of treasure. It's unclear what the treasure is that Troll hoards, possibly knowledge, maybe reminders of actual treasures in heaven, perhaps herring, a ring of power. Troll is indeed a creature of mystery. What we can find out about Troll's mystery treasure box is the mass and the volume. But if we want to figure out if it can float in water, and there's one thing that Monty Python and the Holy Grail has taught us, it's that neither of these things actually determine if we drop the treasure box in the creek after rain, if it will float off towards the Cal-Sag channel or sink to the bottom. Look back through your notes from our first lesson and see if you can determine which property tells us what floats and what the units of that property are. Hopefully you found out that only specific gravity can do that, so our actual conversion needs to be into units of specific gravity, which is actually unitless. We do know two things pretty obviously, mass and volume. We also know that we're interested specifically about floating in water. Since specific gravity is a ratio of densities, even though that is a unitless value, the definition of specific gravity can give some hints for how to use dimensional analysis to solve the problem. See if you can map out a strategy for solving the problem before we talk about it. We can easily look up a density for water, which will probably have units of grams per milliliter if you use a chemistry text. It might also have units of kilograms per cubic meter. You might also notice that it is temperature dependent, but it doesn't change much in the normal range of Earth's surface temperatures. In any case, it has units of mass per volume. If we want to end up with a unitless number, we'll have to divide mass per volume by mass per volume. So we could divide the Troll's treasure mass by its volume and divide that whole thing by the mass of per volume of water, the density of water. Or we could multiply by the inverse. Notice that the density itself here functions as a conversion factor. It gives us an equivalent mass and volume that we can use to convert between mass or volume, or to cancel out another density completely. If we try to set up our work as indicated, we run into a problem pretty quickly. Our actual units work out to kilogram milliliters over gram liters, which is nonsense. So dimensional analysis and keeping track of units here prevents us from forgetting when the units don't actually line up. We could individually convert kilograms to grams and liters to milliliters with separate conversion factors. That would absolutely work. But remember, the prefixes just mean a specific value for a power of 10. So we can still cancel out the units grams and liters, which both have the same grams on top and bottom and liters on top and bottom, as long as we leave their prefix. Perfect. Now we have this value in kilomillis. This is still not really helpful, except if we actually convert them to powers of 10 they represent. Turns out a kilomilli isn't a breakfast cereal, it's nothing. It's the same as no units. This stems from the fact that kilograms per liter and grams per milliliter are actually the same value. Both the numerator and denominator are changed by the exact same amount. Anyway, now we have a specific gravity of far less than 1, which means it floats. If we think about our kilogram as about a half, it is about 1/100th of the 50-liter volume. So 0.5 divided by 50 is about 1/100th. So our answer, just shy of 1/100th, is actually likely correct. This may even give us a hint to Troll's true treasure. Having such a low specific gravity points perhaps to treasure less worldly. What a troll. Some of the problems that dimensional analysis allows us to solve are not really science at all. This mode of analysis can benefit you in unexpected places. Case in point, Troll owes Harry Potter a lot of money, but needs to do a currency conversion to make sure he doesn't come up short. Because you know Harry Potter is going to shove a wand up his nose if Troll comes up shy. Oh yeah, we switched trolls for this one. See if you can walk through the steps of this problem before we go through it together. But to save you a lengthy review of the primary literature, here are two statements of equivalency, courtesy of Hagrid, I believe. The problem suggests that we need to know Troll's debt in nuts, so we need to convert everything eventually into nuts. We're given three types of currency. We could convert each of them to nuts and add them together, or we could convert galleons to sickles, add all the sickles, and convert those to nuts, and add those to the other nuts. Either way, dimensional analysis should help us make sure we do the conversions in the right direction and combine things at appropriate times. I chose the second version, converting galleons to sickles and adding them all together, because the fewer times I need to multiply something by 29, the happier I am. Since I will always be converting a more valuable currency to a less valuable currency, each of my conversion factors has the more valuable currency on the bottom with the equal value of currency on top. I start by converting my 3 galleons to sickles. Then I combine all the sickles. And then I convert to nuts and combine with the other nuts for a total of 1,688 nuts. We can see that we're doing the conversion in the right direction since we're moving toward less valuable units and the number is getting higher. I do want to point out here that we started out with 3 numbers that each had only a single digit, yet I'm still reporting 4 significant digits. The difference here is that currency is generally regarded as exact numbers, and conversions within the same currency system are exact because they're definitional. So each of our numbers is infinitely significant, and we can report exactly the number we get. And we better, because Hermione has already done the math, and Harry Potter knows the exact number too. Hopefully, now you can see that this way of thinking, whether you're already doing it informally or not, can be really valuable when you think about approaching all sorts of problems, even problems in forms for which we don't have a formula. Most of the outcome problems for dimensional analysis are designed in such a way that you wouldn't actually know the formula, but you should be able to follow the units toward a correct answer. Similarly, because dimensional analysis is directed by units, your answers on the dimensional analysis outcome problems will not be considered correct without the correct units.